Hi, everyone. My name is Haoran, and today I'm going to present MuCache, a general framework for caching in microservice graphs. This is a collaboration with Konstantinos, Spyros, and professors Rajeev, Sebastian, and Vincent. So, what are microservices? In old days, servers are monolithic. All processes are tightly coupled and run as a single service. This means that if one process experiences a spike in demand, the entire system must be scaled. Adding or improving a feature becomes more complicated as the code base grows. This complexity limits experimentation and makes it difficult to implement new ideas. To solve these issues, a microservice architecture is introduced. In microservices, applications are built as independent components that run each application process as a service. Because they are independently run, each service can be updated, deployed, and scaled independently to meet the demand. In practice, a microservice application is usually equipped with a service mesh. For example, Dapper, Envoy, Istio. A service mesh deploys a sidecar that is co-located with the service process, and the sidecar will intercept and proxy all communications between different services. In particular, Dapper also intercepts databases accesses so that developers can use the same APIs for different databases. Microservices are widely used in industry. Here shows the core graphs of microservices in 3 big companies. Their number of microservices can go up to thousands or even tens of thousands. Despite the popularity of microservices in practice, there are still many voices of doubt. As we have shown before, microservice offers benefits such as improved modularity and easier maintenance. Without these, a company may face significant losses. Now, despite that, Elon Musk does have a point that microservice applications are usually less efficient than the monolithic ones. There has been many works that analyze the overheads in microservices, and it turns out that the main reason behind it is the high cost of invocations. In a monolithic application, an invocation can be as straightforward as a function call if they are in the same programming language and runtime. However, for microservices, it becomes much more complex. The way production web services mitigate this issue is to add a cache. Caching is a very widespread practice. It has been used in cases where the downstream service don't modify the data very often. For example, here's a hotel and flight reservation website like Booking.com. The hotel and flight service can cache location information provided by the geography service, and the front-end service can also cache results for some popular destinations. Alibaba discovers that 40% of their microservice call graphs are only reach of the depth of 3 because they hit caches. Meta also reports their cache hit rate of more than 80%. A problem when we have caches is that we need to keep them coherent. Every time we have an update to a service database, we need to coordinate among all caches to make sure all cache entries are valid. Even for a multiprocessor, that's a hard problem. And it becomes much harder in the setting of microservices that are distributed across different machines. Unfortunately, the state of the art with respect to caching is rather limited. Developers have to carefully manage the cache for different applications, that they often requires manual configurations of an ad hoc time-to-live eviction time, which usually ranges from seconds to hours. Tuning the TTL could lead to incorrect behavior and could significantly affect performance. So the main problem that we need to solve is to keep caches coherent in microservices and make it efficient with minimal synchronizations and coordinations among services. MuCache is a system that automatically adds and manages caches in microservice applications. The only thing that developers need to do is to declare which of the service endpoints are read-only, meaning that they do not write to any database or have any other side effects. MuCache has 3 key goals. First, supporting the full breadth of the real microservice applications with their dynamic call graphs and multi-language deployment. Second, it doesn't require any application or database modifications to be easy to use. And third, to be correct, meaning that it does not introduce any new behavior compared to the application without caches. At the same time, there is also a domain-specific goal that it doesn't add any overhead on the request processing path, making all cache management off the critical path. So MuCache aims to make microservices cache coherent. But what kind of coherence do we need here? There are multiple ways to define coherence in this setting, but we are only interested in the perspective of the ones who matters the most, the clients that interact with a microservice. You can think of a client as a user using their browser to load a web page. So we want to observe all executions of the cache-enabled application as a client boundary. By observing this boundary, we will end up with the executions like this, where we can see all requests and responses that each client made to the application. We can collect all these executions of the cache-enabled application in a set. We can also do the same in the original application without caches and gather the set of executions as well. A strong correctness condition would be that the set of cache-enabled execution is a subset of the original execution set, meaning that all behavior of the cache-enabled application can also be observed by the original application. However, there is a problem with this definition. Let's think of the following example in an IMDb-like website. Alice issues an upload review to the front end that ends up in the backend service that will append a new review to a certain movie. And later, Bob tries to read the reviews of the same movie using the getReview API. The request first gets the front-end service and hits a cache before the cache gets updated from the downstream service. So the reviews it returns don't include the one Alice just added. Such an execution cannot be observed by the original implementation without the caches, because an irreversible database will always return the latest data. So it turns out that our correctness condition is very strict, and every time we access a cache, we need to coordinate among service caches and database to make sure the cache entries are valid. And while this might be feasible for a two-service chain, this synchronization overhead scales with the size of applications. So is there a better solution? Let's look at this execution in a bit more detail. What does each client really care about? Alice only cares about that her review is uploaded successfully, and Bob only cares reading the reviews without considering if there's any incoming new reviews happening at the same time. Clients do not care about the complete execution from the server's view. They only care about the executions from their perspective. Using this key insight, we can redefine our correctness condition to allow for reorderings of requests from different clients. This is the same insight in sequential consistency, where independent processes do not care about the ordering of requests among them. But why is the reordering allowed here? That's because those kind of reorderings could also have happened in the original microservice applications due to network reordering and delays. Our redefined looser correctness condition now says, given the set of the executions of the cache-enabled application, there exists some reordering across the clients for each of them such that the new set is a subset of the original execution. This insight allows MuCache to push all cache management off the critical path and requires no synchronizations across services. In the paper, we have a complete proof that shows that MuCache satisfies this correctness condition. With this insight in mind, we designed the MuCache system, which adds three components to the microservices: wrappers, cache managers or CMs, and the cache service itself, which can be any cache like Redis or MuCache. We implement MuCache on top of Dapper so that we can take benefit of their unified databases and invocation its APIs. Now let's go through each component one by one. Wrappers are special functions in the sidecar that intercepts service invocations and database operations. They essentially perform two main roles based on two types of interceptions. First, it will check the cache before invocation and return the result without invoking the downstream if there is a cache hit. Second, the wrappers supply necessary context information to the cache manager. This information includes the input arguments for a request, the start and end timestamp for a request, and what keys the request will read and write. So what's a cache manager? A cache manager is a standalone process that processes information from the wrappers and decides when to save or invalidate cache. Each service will have its own cache manager that is co-located with it. And the wrapper doesn't wait for any responses from the cache manager, so the wrapper never blocks the client. The cache manager is the heart of MuCache. It keeps the execution timelines for all requests and where the request comes from. When a request ends, for example, the request B here, given that request B only read Y, the cache manager will check if there is any write to the same key during the request B's time span. If not, it will send a save message to the cache manager of the upstream service, asking it to save the result locally. When later another request C overwrites Y, the cache manager will send an invalidate message to all upstream services that cache the results related to Y. This is the simplest example. For more complex and interesting cases, please check out our paper. Now, let's look at the benefits that can be achieved with MuCache. We implement 4 open source microservice applications, 3 from desktop benchmark, including hotel reservation, movie review service, and social media. And another one, online boutique, is a demo from Google Cloud. We compare MuCache with 2 baselines. BC stands for backend cache. It only caches before the backend database, for example, adding a Redis before the MySQL database. It doesn't cache inter-service calls. And another one is the TTL infinite, which is an unrealistic upper bound where cache entries never expels. The takeaway of this graph is that MuCache can outperform BC on median tail latency and throughput, and it performs very closely to the TTL infinite with up to 20% higher median latency and 5% lower throughput. We also evaluate the deployment cost of MuCache on the hotel reservation application, which contains 6 services, shown in x-axis. We measure the CPU, memory, and network usage and compare it with the baseline. From the figure, we can see the CPU usage breakdown. MuCache itself introduced around 13% of CPUs on average, but it can save more CPUs for the application because of cache hits, especially for the backend services that do not modify the data very often, for example, the rating service here. And we also have an efficient garbage collection algorithm that reduces the metadata in the cache manager to less than 3% of the cache size. MuCache can also reduce the total network usage by 27% due to local cache hits. So to conclude, MuCache is a caching system designed for microservice applications. It has a proven correct protocol, and it's easy to use that works with production service meshes, and it has low overhead on the critical path. And our code is open source, and thank you. I'm happy to take any questions.